So I'm Douwe from Willigen, and together with Erwin, Mostert, and Michiel Pertijs, I worked on an in-air ultrasonic gesture sensing system with MEMS microphones. We work in the electronic instrumentation laboratory of Delft University of Technology, and yeah, worked on this past year. So, sorry? Okay. Why would we use in-air gesture sensing? Now, first of all, it's of course intuitive, and if you want to, for example, switch pages on your phone when you are following a recipe, it's really useful to have to work with your phone without touching it. So, for example, such an application is it really useful to have in-air gesture sensing system. Current systems are mostly optical, and some problems that you get with this is, for example, that they are sensitive to sunlight, and most of them also consume a lot of power. So this is also a reason to find another way to have in-air gesture sensing other than optical systems. Yes, and our solution is to use ultrasound for this. So the way we wanted to do this is by sending a pulse with one piezo speaker and receiving the echo with an array of microphones and analyze this echo. So there are some difficulties we have to work with. First of all, we need to determine the distance of the object. That's fairly easy. We also need to determine the direction of the echoes. And after that, we need to recognize the gestures from these echoes or moving objects that are in the field of the microphones. And for ourselves, we set the goal to do this all with commercially available components. The first challenge, determine the direction. Oh, that was the second challenge. The first challenge was fairly easy, so I'll get later to it. Is to determine the direction, and we do that by means of beamforming. Beamforming works by steering an array of microphones in a certain direction. So, for example, if we have a sound wave coming from this direction, and we steer the array with these delays in that direction, all these signals add constructively to a large amplitude signal on the output. And if, for example, the sound wave comes from another direction, like, for example, from the top here, and we still steer in the direction here, the signals don't add constructively, and you just get a low amplitude signal from it. Another thing which is important here is the microphone pitch, because if you have a microphone pitch that is fairly large, like, for example, the wavelength of your signal as a pitch, you get pretty large grating lobes. This means that you will get ghost objects on more angles than just straightforward. If you have a smaller pitch, like, for example, half the wavelength, you get a little bit wider directivity here, but you don't get the grating lobes, and this is what we like here. Yeah, because of this small microphone pitch, we need also small microphones, of course. First of all, we want sound that is not audible, so it needs to be more than 20 kilohertz. So we chose to use a piezo transducer for this, which has a center frequency around 40 kilohertz. And we need to find microphones that are half of the wavelength of that at max, and that's 4.3 millimeters. Yeah, this is, for example, such a piezo transducer. They are 10 to 20 millimeters. That's way too large for this pitch. So we found the MEMS microphones really useful for this purpose, because they are in the range of the 4.3 millimeters that we need. This is a close-up of one of those MEMS microphones, and you can clearly see the membrane here. It's broken, and in this case, that was why we opened the case of the package. Yes, this is the block diagram of our system. Yeah, we have here the piezo speaker that sends a burst of 4 pulses. A single speaker, is it? It sends a burst of four pulses, and the reflection of it is received by 7 microphones in an array. It is high pass filtered and a little bit amplified, and after that it's converted to a digital domain with the ADC. Here are some figures. So we have 11 times our gain of 11 gives us a 3-volt peak-to-peak voltage. So that's fairly nice with these microphones, and they don't have an internal amplifier. And that's only with those 4 pulses of the piezo transmitter. So yeah, we made 2 circuit boards for these, one for the analog circuitry and one for the digital part, so the digital conversion. So here we have the piezo transmitter and our array of microphones with the 4.3mm pitch. We have the high pass filters, the op amps, and yeah, here's a connector so we can stack the PCBs. And finally the ADCs, which convert the signal to the digital domain, so we can use it in an FPGA to analyze it. So the part in the FPGA here is, now of course the pulse generator is also in the FPGA, so we can synchronously do this. We have beamforming, we did it parallel, so we have 40 parallel, or 60 even in the last case, parallel beamformers, so we can do this in real time. And we have then the real-time B-mode image of what's in the field of the microphone array. And after that, we do peak detection on the B-mode image to find gestures in this plane. So this is how we construct the B-mode image. We do that by yeah, the beamforming principle again. What you see here is the distance, and here are the angles in the plane of your microphone array. So yeah, this is one object, and here's another object. So here were 2 hands hold yeah, on top of the microphone array. And yeah, here are the beamformers that work in parallel. How do we detect the objects? We do that yeah, by peak detection. If you have the cross section here at the point of A, you get more or less this figure. And just by getting a threshold and find out which signals are above that, and that's the closest here, we say, oh, that's the peaks in this direction, and we also get the peaks in the vertical direction, so the distance. And this cross section gives the squares here. And if we combine these, we finally get one peak that is more or less representative for the location of the object. Finally, these positions are used to get more or less the gesture that is made with the hand, for example. If a start condition is met, so this is an angle here, and this is again the distance. If a start condition is met, like if we put the hand on the right here and move it to the left, while it stays in this green region, it will still be valid. And finally, if it comes in the stop condition region, it gives an output to the PC that there was a gesture, and it can, for example, control a slideshow at this moment. And yeah, so it detects simple gestures. This is an image of the results we got. We had the PCB put here, and we moved the cylindrical object. First we moved it in this direction, so these are the blue points here. The cylindrical object was like 8 centimeters in diameter, and after that we also moved the object in the horizontal direction, or it's top view here, so in the direction perpendicular, parallel to the PCB. And yeah, we get a very clear, yeah, good results. They are a little bit off sometimes, but this is not really necessary to detect the gestures, because you just need to have the motion of the gestures and not really the accurate position of it. Finally, we compared these results with other systems that are made in past years. Prisbilla, for example, made a system with PMUDs. It was integrated, and he made a self-designed chip for that with a fairly high frequency. Furuhashi also made a similar system with MEMS microphones on a PCB implementation with the same frequency as we did. The difference is that they had Chris Billa had a more expensive system because he needed to make the integrated circuit for it. And we use off-the-shelf components and get similar results with this system. Finally, the conclusion is that we have a working prototype. We can detect simple gestures with it. Here in the image you can see me with my hands above the PCB here, and you have the two hands in the B mode image on the screen. We do this real time, and it's very affordable because it's all built with off-the-shelf components. Thank you for your attention.